So about 2 years ago, my primary laptop, my daily driver, stopped working properly. The battery did not hold charge anymore, and therefore it's pretty useless as a laptop. I had a business trip coming up in a week, and I wasn't sure if I can get the battery service within that time frame. Therefore, I went to eBay and purchased a backup laptop. That was the laptop that Sumit just mentioned. Since I intended this to be as a backup, not my primary laptop, I decided to pick some very cheap laptop, a used one, $300. I only have half a CPU cores and half as much memory. And since it's a used laptop, the battery life wasn't the best. I could probably use it for half a day before I need to find a charger. So I brought this laptop with me for my three-week business trip. Once I come back home, I was actually torn. On one hand, this laptop is by any measure is inferior to my primary laptop. But I didn't feel that I was crippled. In fact, I feel that I was liberated. For instance, since the battery life is not that fantastic, I didn't start the day by looking at Hacker News, Reddit, or Slashdot, or whatever toxic website of your generation, right? I immediately got to work. And the laptop is fantastic for day-to-day browsing or even my usual coding tasks. I don't feel that I need to reach for a more powerful laptop. And sometimes that's how it works in our life. Sometimes we're attracted by this new shiny object, but in some cases, a small laptop, could be as productive as a more powerful one. And that's what we're going to discuss today. Just like in the world of large language model, we have probably the state-of-the-art models such as GPT-4, extremely powerful, really useful for many different things. But at times, you don't need to reach for GPT-4. Now, excluding the cost issue, if you have access to some smaller model that you can run on your laptop, then it opens up a whole new possibility, right? For instance, maybe you really care about your privacy. You don't want your data to be sent to any cloud service out there. Maybe you want the model to be small because for what you need, it's more than sufficient. As long as the answer comes back within a reasonable time, I think that's more than sufficient. So today I'm going to try to share a couple of tricks that I discovered while working with a small model. It's funny to refer to small model as a small LLM because LLM stands for large language model. The time reference is also important here. Today, we call 3 billion model as a small language model, right? 2 years ago, 500 million model is a very big model. And with the power of the computing devices this day, you can comfortably run 3 billion or 7 billion model on this M2 Pro. If you have M2 from MacBook Air, you can still run it, just slightly slower. And with the trickle-down effect, I expect that in 2-3 years, any modern laptop will be able to run 3 billion or 7 billion model without any issue. So first thing first, there's this new paper, a beautiful paper called Retrieval-Augmented Generation for LLM, a survey. Please take a look at this paper. There's a lot of technique outlined in this paper. It will take hours to digest through that. Most of them I also don't know. And the other thing is that if you've seen this meetup before, everything that I'm gonna be showing to you today will be available. This called Pico Jarvis. Jarvis is homage to Tony Stark, and Pico is because it can do only 10 to the power of -12 of the real Jarvis. It is going to be open source. I'll share the link. Oh, by the way, I'll share the deck, and you'll probably get the email from us, either today or tomorrow. So that's the main backend that will use the small model, yeah. And then as the inference engine for this model, we're going to use Llama CPP. Very easy to compile and run, very popular. And then as the choice of the model, I will encourage you to try Phi 2. This is the latest model from Microsoft, announced a few months ago. Basically, Pico Jarvis is the RAG demo. It is not very long, it's 400 lines. And it can do three things, right? It can try to answer your question from its memory. And if you ask some question about the weather, is it snowing today in Palo Alto, then it's going to go and fetch a weather API, get the data, and then display the answer. or it will search the PDF. Now for this demo, I supply Pico Jarvis 30-something page PDF that I created by going to Wikipedia page of the solar system and then print it as PDF. So nothing fancy, but this should serve as a basis if you haven't done RAG before on how to build RAG. Oh, by the way, there's no framework here, so everything is as bare bones as possible. So cut out the middleman. This is the repository. Phi 2 was announced a few months ago, and it is fantastic because the small model that I played before, Orca, slightly larger than Phi 2, but its reasoning ability wasn't that good. So you could use it for RAG, but it will fail very quickly. Whereas with Phi, there are going to be a few techniques to make sure that you push the limits of Phi intelligence, despite this having only less than 3 billion parameters. So for a refresh, let's review a bunch of concepts. So there's something called zero-shot prompt. Maybe I should demo what you will expect if you download and run Pico Jarvis. So as you download it, I have some automated setup so that I don't need to type all this question. So you should be able to answer the question, who is the CEO of Google, just from the memory. And if you ask a question about anything about solar system, and it will look up the PDF, extract the relevant part, and use it to compose the answer. We'll see the diagram on how it does that. By the way, this is all running on my laptop. I'm not connected to, I'm connected to internet to display my slide, but all this inference happens on the laptop. In other words, in the airplane, you could do this, and it will answer it for you. Okay, so this is the basic zero-shot prompt. What does it mean? And this is the bare-bone diagram of any chatbot engine. You have the engine, and then the user throw a question, a query, whatever it is, and then it will send this directly to LLM of your choice. In my case, Phi. Could send it to GPT-4 if you want, and then supply with some conversation history so you can do multi-turn. Multi-turn is fantastic because it will be able to refer to your previous chat. I think we kind of take it for granted, but this is something wasn't really common a few years ago. So the way it looks under the hood is if you have this kind of question, technically this is called the two different roles of the message. That is the user message, and this is the assistant. So the LLM is supposed to produce the answer in a form of a message as an assistant. But if you're a pro ChatGPT user, you might realize that there's something called the system message. Very common term for this is prompt engineering. So you can change the behavior of the model, the way it answered that, the way it tried to come back to you by tweaking the message. That's why, although my question is 5 words, the answer is very long because I said answer verbosely. If I change this to answer concisely, the answer is as concise as it could make it. Now, this is of course fantastic because we just rely on LLM to provide the answer. However, sometimes it falls short of our expectation, particularly for small model. Given that it has limited brain capacity, less neurons compared to, let's say, GPT-4, obviously sometimes it doesn't answer the question correctly. For instance, when I tried this, does anyone know? Pretend this is a trivia game. Yeah, but if you give this to Phi, not very useful, right? Because Captain Kirk's first name is Kirk. Well, first is wrong. Second, we already know that. Now, this is where we enter something called chain of thought. The idea is the same thing. Instead of just throwing this question to the LLM randomly and hope it come back with the correct answer, we tell the LLM, no, essentially, think harder or think step by step. And that's precisely what is being outlined in these 2 papers, usually a very good canonical reference for anyone who wants to learn about chain of thought. For instance, we can tell the LLM, this is the system message, the prompt, you might say, well, don't answer right away, right? Basically think. Pretend that you have access to Google. It doesn't. Just pretend. If you have access to Google, how would you answer this question? And then think step by step. So by doing that, and this is the premise of that paper, by doing that, apparently the likelihood that the model come up with the correct answer increases significantly. In this case, I'll answer James, and I'll show you what happens behind the scene. But let's take a detour. So this is something that is, I discovered, very important when you work with small model. If you ask the model, instead of the model comes back with a text or a string in programming terms, tell the model, well, come back with some data formatted in JSON. And this has several benefits. This is what I call as native JSON or JSON born. Hopefully you got the reference. Basically, we ask the model to pretend that it has access to Google and then outline how it's going to solve the problem. So what is the thought? And which tool do you use? Obviously, there's only one choice here, Google. And then if you are about to type something to Google to find the answer to the question, what will be the keywords or the key phrases? And then finally, the answer. By the way, in this case, this is all make-believe. The model doesn't have access to Google. It's just pretend it could do all these things. And that's why when you saw the previous slide, the answer James, it's actually going through this iteration. Right? Oh, yeah, I'm going to try to find the answer. This is what's not right. I'm going to use Google. By the way, I'm going to type Captain Kirk's first name, and Google is going to come back with James. This is all in the model's imagination. And that's why what we see at the end is the correct answer. So we can take chain of thought later on as something that we can use to help further on how the small model will reason. At the end of the day, small model has limited reasoning and capacity, and therefore sometimes the answer is wrong. For instance, this is correct, August 2012, Voyager 1, but 1 and 2, they're separated by a couple of years, which means this is not possible. So this answer is wrong. This is why we need RAG. Instead of trying to recall from the memory, we will ask the model, hey, for this type of question, try not to recall from your memory and use the reference document. Retrieval-Augmented Generation. There are two words there, and there are two big steps there, literally, the retrieval part and the generation part. Again, there's some query, there's some conversation history, and we will try to retrieve some additional reference information, whether it's from a database, an API, a document, what have you. And then once we collect some information about that question or something that related to the question, we're going to use LLM to generate the answer for that. This is similar to going to the library, right? I don't know anything. I want to know about something. 100 years ago, there's no internet. You just go to the library and then find the most suitable books or reference for something that you want to study, and then look it up. And that's why you can study that subject or answer that question. Exactly the same thing what RAG is doing. Surprisingly, the generation part is super easy. The retrieval part is the hardest part. So what the generation part is doing is basically this. This is against system message, a prompt. You tell the model, hey, you have this random question from some loser. Here's a bunch of text. And if you have this text, how would you answer the question? Right? Now, let's say I want to ask this question. Is it currently snowing in Palo Alto? And the answer is no. Behind the scene, in this case, Pico Jarvis will go and fetch the weather API and then supply these bits of information, right? The pressure, the temperature, the humidity, and so on and so forth. And given this information, and given the original question, the model concludes, of course, it's not snowing here because the weather report here doesn't indicate whatsoever that it is snowing. So the model is not smart. It relies on additional reference document to form a conclusion. So the generation part is easy, as long as you manage to get the reference document, and ideally not that long, because maybe you know this, but if the prompt or the message is getting longer and longer, it takes time to come back. And if you use expensive model, yeah, that's going to be not very cheap. So ideally, just like you go to the library, you don't go to one shelf after another and then read every single book. You try to find the most relevant parts and reference in the library, and then use that as your reference. So apparently one important thing about working with small model is query transformation. This has a lot of implication, and there's many applications. For this particular use case, I use the query transformation to simplify the question. This is important because usually small model will not be able to cope with long text or long conversation history, or in this case, a multi-turn conversation. Suppose you ask this question, what is a dwarf planet? And they'll come up with the answer, whether it's through RAG or from the memory, right? And then, well, that's good, but I want an example. And then you say, give an example. Right? So GPT or other small models, 7 billion, can understand this, that essentially what you mean is, give me an example of dwarf planet, right? But Phi or smaller model, sometimes will get confused, not all the time. And they'll come up with this answer, right? An example is a thing that demonstrates a particular feature or property. So technically speaking, this answer is correct. It's just not what I want. So to work around this problem, we kind of need to transform the query, the given example, into something that is a bit more accurate and meaningful for the model. This is something called, the problem of a language assistant. Again, we tell the model, pretend they're your language assistant, and you have this conversation history. And here's the last question from the user. How would you reformulate that, and why? Right? There's an explanation. So if you do this to my previous example, given this history, and this is the last question, the model internally will rewrite that to, can you provide an example of a dwarf planet? Right? Maybe if the model is trained differently, it's going to ask, please. Right? In other words, what the user type give an example is not what the model sees. So this is the first step, query transformation. After this, then we give the entire thing to the model. Right? So again, give an example. Internally, it will look like this. Well, rephrase this question. This actually means, can you provide an example of a dwarf planet? And why? It's because so and so. Right? Of course, this is thing that you don't see. Or if you play with Pico Jarvis, you don't see this at all. In other words, what the model sees is this question. And of course, it will happily answer that question because it's not difficult to answer that. So query transformation, something that is very powerful to nudge the model to come up with an answer for not the raw question or query from the user, but something that has been modified a little bit for clarity. The next thing is height. This is very important for document embedding. The source for this is the so-called hypothetical document embeddings paper, precise zero-shot dense retrieval. Beautiful paper, has a lot of implication. Everyone should read it. The idea is very simple. The way in the retrieval process we find the relevant document is usually by finding the semantic similarity between my question and the reference document. Right? For instance, again, the previous case, what is a dwarf planet? Right? If I have a PDF, and this is exactly the PDF that you enjoy if you check out Pico Jarvis, there's 30 pages and some 400 sentences in the document. So the first step for RAG is the retrieval. If you find semantic similarity between what is a dwarf planet, the most similar sentence is sentence number 434, which basically says dwarf planets are considered planets by some planetologists, but not by the IAU. It's useful, but apparently, if you read one by one all the sentences in document, this is not the best answer to this question. In fact, this is not the best reference. Right? So what do? Apparently, with the idea of hypothetical document embedding is that, given this question, just feed it to the LLM first, see what the answer is. It doesn't really matter if it's wrong. Right? And in this case, Phi 2 will come up with this answer. And then if you find something in the reference document that is as close as possible semantically to this answer, this hypothetical answer, you'll come up with actually one sentence before that, which exactly gives the definition of a dwarf planet. In this case, the sentences look the same because, of course, every language model is trained by a Wikipedia article, and it so happened that my reference document here is from Wikipedia. But even if the answer is completely wrong, the numbers are wrong, the dates are wrong, it doesn't really matter because the likelihood that this is semantically more similar to some portion of passages in the document is higher than the original question. So that's an extremely powerful technique to make sure that you find the most relevant document. Because remember, in RAG, the retrieval is the key, not the generation. If you retrieve the wrong document, then all bets are off. Next is key phrase search. And it's kind of already alluded in the earlier deck. So if you play with Copilot from Microsoft, not to be confused with GitHub Copilot, if you type a question, and, while waiting for the answers, you can see something such as searching for coldest planet in the solar system. You can see that this is a form of query transformation, right? Coldest planet in the solar system will be exactly the search term that I'll enter into search engine. In this case of Copilot, it goes to Bing, but you can imagine it will work with any search engine or any search system of your RAG reference, right? And then it provides some citation too. In other words, during your retrieval phase, do not try to blindly use the original question as your reference for retrieval. Use something that resemble some key phrases. And you can expand these key phrases. In this case, there's only so many ways to define a planet. You can say celestial bodies, heavenly bodies, and so on and so forth. So if you know all those terms related to the planet, you can also search that in your document. There's a beautiful paper called Splayed. This technique is called lexical expansion. As soon as you manage to get the absolute keywords, key points of the search, find other related terms, insert that in your document as well. This expands the horizon of the retrieval, and therefore, even though your reference document might not exactly mention the word planet, maybe it mentions celestial bodies, you'll get it in the retrieval stage. But what if you end up with a lot of search terms and then a lot of references? How would you do that? This is something that search engine have been doing for a long time. By the way, in this demo earlier, in this earlier slide, you can see that this input is a form of key phrases. In other words, if I have a reference document to find the answer to this question, I'll search for any sentences that has all these words, Captain Kirk's first name. This is what we experienced from any kind of search system in the last 20 years. Right? If you have the lexical expansion of the key phrases, you can find all the relevant parts in the document, but that could be a lot, there could be very many. So that's the first step retriever. Then you can do re-rank to figure out which one of all these, dozen or so passages is the most relevant to answer the question. So the first step, if it's done through keywords, it can be very cheap. Does anyone here know, or is anyone here a fan of regular expression? Yeah, don't use that, you have another problem. So there's a lot of technique that can achieve very fast and accurate retrieval given the keyword. You don't have to use LLM or even semantic search for that. So last but not least is intent classifier. Is it a muffin or not? It's always confusing to see this picture. Now with big model, usually to implement some sort of tool or function, we use the pattern called reason and act, shortened to REACT. Nothing to do with the front-end framework. The idea, which works very well with 7 billion models or above, is, again, coming back to the weather example, this model doesn't have any weather model of any part of the world. So it needs to, we need to assess it by supplying the actual weather information of Palo Alto right now. So the reason act pattern basically says, well, first, let's ask the model how it's going to solve this problem. This is the first stage, the reason act. It's going to dump all this called chain of thought, right, in the original JSON mode, perhaps. If I have that question, is it snowing in Palo Alto? Then I need to find the weather report for Palo Alto. So it's going to say action weather Palo Alto. We don't care about the answer because obviously this answer is wrong. We just want to know how, right? Doesn't care about the what. And then the backend, in this case, Pico Jarvis or whatever your rack system needs to actually fetch the weather information and supply it then in the form of the sentence or longer or what have you, right? And then we'll tell the user, okay, now I've acted on your behalf. Please continue the inference. Right? So we need two calls to the LLM. Well, this works beautifully for large language model, right? But apparently for 5 or 3 billion model, this is way too much. Trying to infer whether it's a weather, it's a solar system, it's a general question, and then trying to extract the keywords, it's too much. So again, this works fantastic in a 7 billion model. There's a decision path here, right? This is a question about weather. Okay, what is the location? Find that. Or is it a question about anything related to PDF? Okay, now I have to look that up. So 7 billion model or above can do this thing in one step. small model couldn't do that. So the trick is to build a classifier first that don't care about what is the keyword and key phrases there. We just want to decide, is this about weather? Right? Is there any location on Earth mentioned in this question? If yes, okay, now we give it to another stage. People call this entity recognition. You can use LLM, you can use traditional NLP to figure out what is the location meant by the user, and then we proceed. But if it's that the question that have nothing to do with the weather, then let's do the usual chain of thought or JSON of thought or what have you to find out what are the key phrases, and then in the second part, we'll do the usual retrieval, finding relevant passages using vector similarity and such. In other words, this needs to stack, because the first challenge for the small model is just way too much, it will collapse. Instead of that, we build a simple one task only classifier, and then after that we branch. We have to be careful though, because for instance, if the question is, how's the current weather there? And I just ask about the capital of Indonesia. If you just feed this question to an entity recognition, it will not get the location. There's no location there, there's only a there, right? Again, the trick is, well, feed this to query information. So internally, this question will be phrased as, how's the current weather in Jakarta? And then the subsequent step will be able to extract that location without any issue. Very important for a multi-turn conversation, because that gives the very smooth experience. Yeah, that's all the technique that I want to mention. In short, treat this model, this small language model, not as one model that can do a lot of things. It will collapse, it will not be able to do that. But combine all these models, or not all these models, all these instances with the small models with different prompt, with different system message. So it forms a pipeline. So one stage doing one thing really good, and when you combine that, when you chain that, when you architect that properly, it gives the impression that, oh, this small model is actually fantastic. And remember, because it's small, the inference time is so fast. Even if you cascade 5 or 6 stages, it's still going to come back faster than, let's say, GPT-4. All right, that's all I have. And you know the drill. If you like this talk, please follow me on LinkedIn to find more information about small language model. If you don't like this talk, don't panic. You're part of the control group. So please follow Summit. Thank you.